Hello guys, before we move on to the next question, we need to take a look at special theory of relativity. So basically, there are two postulates of special theory of relativity to begin with. The first postulate is all inertial frames are equivalent. And the second postulate is speed of light is the same in all inertial frames. So what do we mean by all inertial frames are equivalent? First of all, we need to look at what is an inertial frame. An inertial frame is a coordinate axis with x, y and z coordinates and a cloak attached to it. So basically what this postulates tell you is that regardless of it being any inertial frame, say you have an inertial frame xy and with time coordinate t and another inertial frame which is traveling with a velocity v with respect to our inertial frame, all the physical laws will be the same in both the both the inertial frames. For instance, another way to put it is there is no particular inertial frame that is preferred by the universe. That is, there is no absolute inertial frame which you may distinguish from other inertial frames. So all the inertial frames are equal. The next thing is speed of light is the same in all inertial frames. That is, light has a constant velocity c in all given inertial frames. This also means that there is a speed limit in this universe. So say for instance, a person A who is standing in an inertial frame, never mind. There is a person A who is standing in an inertial frame and he pushes a cart. Now, at a velocity, he pushes a cart at a velocity v, in which we have our second person. Now, the second person throws a ball at a velocity v dash. Now, suppose the velocity that was imparted onto this particular cart was something like 0.6 velocity into velocity of light, 0.6 into c is the velocity of light, and this second guy, that is the person B who is sitting in this cart, he threw the ball at a velocity v dash which is equal to 0.6 into c according to him. Now, this guy threw the ball at a velocity 0.6 into c as far as his coordinate axis is concerned. Now, based on our Newtonian mechanics, how we would do is both the velocity of this ball with respect to this guy will be counted as 0.6c plus 0.6c, which will become 1.2 into c. This is not allowed in special theory of relativity. In special theory of relativity, you have an upper limit on speed. And how you do this math, I will come to it soon enough. But before that, let's talk about its concept. So, what happens is, according to this guy, alright, this guy is moving at a very high speed. So, the total velocity, in order for it such that the total velocity is not greater than c, the time as observed by this the person in this inertial frame and this inertial frame is different. That is, the flow of time is different for both these inertial frames. So what this guy sees as 0.6 into c, that is, when this guy measures the relative velocity between when this guy measures the relative velocity of this ball and velocity of this guy, which is not 0.6, and he subtracts it from this velocity from the velocity as observed by person A. If that happens, then he will find that it is less than 0.60. So no matter what, the velocity of light will not be exceeded in any frame of reference. Now, the next thing that we need to do is mathematically formalize all of this. So, mathematically speaking, I will not be deriving it entirely because our purpose is to know things that are sufficient for CSIR NET exam. So, the thing is, say we have an inertial frame xy, alright, and it has a clock associated with time t. Now, say we have another coordinate axis which is given by x dash y dash, and a time associated with this coordinate axis t dash. That is, in this inertial frame, this coordinate axis value of x equal to 0 when it is at this starting point. Now, another thing that I need to say is, say we are considering two inertial frames, and this second inertial frame is moving with the velocity v with respect to this inertial frame. Similarly, value of time t we assume is equal to 0 when, according to a person in this inertial frame, if he finds that the origin of this inertial frame and this inertial frame are coincident. So that is our t equal to 0. That is when we start counting our time t. Similarly, time t dash equal to 0 for a person in this coordinate axis. For a person in this coordinate axis, time t dash equal to 0 when he finds that the coordinate, the origin of this coordinate axis is coincident with the origin of this coordinate axis. Remember, take a look at that. I said that we are measuring time differently for both these guys, because had it been a regular case, we would have considered it both to be equal, which is our Newtonian mechanics. So, in Newtonian mechanics, we use Galilean transformations. Alright. So, what are Galilean transformations? Say, I have a point P. Say, I have a point P, which is denoted as x comma y, or in this coordinate axis, and or x dash comma y dash in this coordinate axis, and we are measuring it at a time t in this coordinate axis. We don't know what is that, the value of that, what is the corresponding value of t dash in this coordinate axis. If we are looking at Galilean transformations, that is in the transformations that are associated with our Newtonian mechanics, what we find is the value of x dash, that is the value of x coordinate of this point in this coordinate axis, x dash is equal to the value of x minus v into the time taken, for this in this coordinate axis, right, which is vt. This distance is vt. Now, this is how we calculate the coordinate. This is how we do coordinate transformation in Newtonian mechanics, and this is known as Galilean transformation. So, take note that the time is being counted as same. In Newtonian mechanics, if time t is passed, like when this reached at some particular, when this coordinate axis has reached some particular distance, the time t that has passed in this coordinate axis and the time t dash that has passed in this coordinate axis are both considered equal. So t dash equal to t. This is Galilean transformations. But this is not the case when we come to special case of relativity. In special case of relativity, we find that the time t dash need not be equal to t. That is, as I said earlier, the time makes the adjustment so that time adjusts itself, or time we call it time dilation. Time dilutes such that the net speed of the universe is never crossed, so that the value of c remains same in all given inertial frames. So how that works is I'll be rubbing this now. In Lorentz transformations, what happens is this value of x dash will be linked with the value this point p will be measured in x dash. How it will be related to the coordinates x, y, and t in this coordinate is given as x dash equal to gamma into x minus vt. Alright, and t dash equal to gamma into t minus xv by c square. Now gamma is a term that will that will repeatedly come when you consider special theory of relativity, and the value of gamma is given as gamma equal to 1 by root of 1 minus v square by c square. So this gamma is the person. So this gamma incorporates has also a value of v in it. Remember that. The next common constant that can occur in special theory of relativity is beta, which is v by c. So since we have gamma equal to 1 by root of 1 minus v square by c square, we can take this v out, we can rearrange this and write v in terms of c and gamma, which is c equal to root of gamma square minus 1 by gamma square into c. V equal to root of gamma square minus 1 by gamma square into c. Now, this is how the transformation occurs, and we call this particular transformation as Lorentz transformations. There is a derivation how you can arrive at this, saying that there will only be linear terms, there will not be square terms associated and such, and corresponding derivation can be achieved. But I am not going through that. Now, when we take a look at this, the next thing that we will have to take a look at is how, since we were given with values of x dash and y dash, and the time was given in t dash, and we need to transform it into the coordinate into the inertial frame for our xy. So we know the value of point p in x dash, y dash, and t dash in terms of x dash, y dash, and t dash, and we need to find its corresponding coordinates in xy coordinate system. So how do we do it? To do that, it's basically the same. Alright. See, if this guy is moving with respect to this guy with a velocity v, then according to this inertial frame is moving backwards or at velocity minus v with respect to this coordinate system. So x will be equal to gamma into x dash minus of v into t, which becomes x equal to gamma into x dash plus vt. Similarly, t equal to gamma into t dash minus vt, that is plus minus vx by c square, that will become plus v x dash by c square. Yeah, here was dash. So this is how we do Lorentz transformation. Now, another thing that we can see is that we have to look at is time. When it is not just coordinate axis and time, so that we do transformations on. Quantities other than x that position coordinate and time can also be subjected to transformations. So another quantity that would more likely occur in your problems is energy and momentum, E and X. So how this works? Even in this case it works. So something dash, so it's how you will be able to do it. Something dash, okay, something, I am not writing it down. Something dash equal to gamma into that something minus V into the other thing. Alright. Now, in case, now we'll check whether the dimensions of these both are equal. If it's not equal, we divide by c square. This is how we do it. Now, let's take something as our energy. E dash equal to gamma into E minus Vt. Now, the dimensions are matched. Similarly, P dash, Px dash equal to gamma into E minus Ve. P minus Ve. Now, if you take a look here, you can see that the dimensions are not matched. So, in order to match the dimensions, we divide by c square. It's the same thing here. This x dash was for something and t was for the other thing. We match the dimensions. Now, the next thing that we will look at is velocity transformations. Say, for instance, this point P of ours was not moving, was not stationary. It is a moving object. Alright, so this point P is moving. Then we have our transformations were the same, x dash equal to gamma into x minus Vt and t dash equal to gamma into t minus Vx by c square, and we take differential on both the things, that is dx dash equal to gamma into dx minus ddt and dt dash equal to gamma into dt minus v dx by c square. The next thing that we do is I take this as my equation number 1 and this as my equation number 2. I am dividing equation number 1 by equation number 2. What I get is dx dash by dt dash equal to I will be able to take this dt outside. Here also I will be able to take dt outside. Then gamma dt by gamma dt, which will get cancelled, into dx by dt minus v by 1 minus v dx by dt divided by c square. Now these both guys will get cancelled and we get dx by dt minus v by 1 minus v into dx by dt by c square. Now, in this case, we knew that the velocity of this point P, that is dx by dt, we knew that, and we know the velocity with this coordinates axis is moving. Then we are able to find the value of velocity of P with respect to this coordinate. Similarly, earlier as I have said, if I am finding the value of dx by dt, then from here what will happen is dx, if I am finding dx by dt, then this will become dx dash plus dt dash, then dt will become dt dash plus dx dash, and when I divide 1 by 2, I will get dx by dt equal to dx dash by dt dash plus v by 1 minus dx dash by dt dash. So how this equation helps is, if you know the velocity of this point P with respect to this inertial frame, and you also know the velocity of this inertial frame with respect to this inertial frame, then you can find out the velocity of this point with respect to this inertial frame using this equation. Alright, this is velocity transformation or addition of velocity in relativistic kinematics. This is also very important. The next thing we will be taking a look at is length contraction and time dilation. Say for instance, you have an inertial frame with x, y and t as coordinates, and another inertial frame with x dash, y dash and t dash as coordinates. The second inertial frame with x dash, y dash and t dash is moving with velocity v parallel to x-axis. Now, what we are taking a look at is, say we are placing a rod of length L0 at rest in our x dash, y dash, t dash axis. So, the length of this rod as measured by a person stationary in this x dash, y dash inertial frame would be L0. Now, we want to know what the length of this rod is as measured by a person in xy inertial frame. For the person in xy inertial frame, this rod is moving along x-axis with the velocity v, since it's in this x dash, y dash inertial frame. Now, let's take a look. X dash equal to, alright. How do we take, before we do that, how do we take the measurement of length of an object? We take the measurement of length of an object by simultaneously measuring the coordinates of both its endpoints and then subtracting one end from the other. So, what we are actually doing is, we are measuring both these lengths in time t. Okay. We are measuring both these lengths at a time t in this inertial frame. Alright. So so what is constant to us? What is constant to us is this time t. So that is the reason we are taking x dash equal to gamma into x minus vt. Okay. Now, the value of x dash at this point is L0. Okay, so L0 equal to gamma into x of L0, x of L, say for instance. That is the value of x coordinate, the value of coordinate of this point in xy initial frame, that is x of L minus vt, and if you are taking this point, that is in 0 0. So for that point, x dash is 0 equal to gamma into x of 0 minus vt, where x of 0 is the value of this point the value of x coordinate of this point in this initial frame of reference. Now the length can be measured as L0 equal to equation number 1 minus equation number 2, which is L0 equal to gamma into x of L minus x of 0. If the measured length of this rod in this initial frame is taken as L, then that will be gamma into L, or that length will be L0 by gamma. So, for a person, if a rod is moving in a direction, then the length, if a rod kept parallel to a direction is moving in that direction, then for that person, the length of that rod as observed by that person, L, will be equal to the inertial length, the length of that object, the length of that rod when it is kept at rest, L0 by gamma. The next thing that we will be taking a look at is time dilation. Well, this equation and this concept are both important, very important, as many forms of question can be asked from this section. An example would be, say for instance, this rod is replaced by a sheet of mass of length L0x along x-axis and L0y along y-axis in the initial frame in which it is at rest. Then we are measuring its length in our xy initial frame, and the length along x-axis in xy inertial frame is L into length along y-axis in xy inertial frame is Ly. So area in xy inertial frame is Lx into Ly, which is equal to L0 by gamma, L0x by gamma into L0 y. Now, its motion is along the x-axis, so only Lx is affected, only the length in the x direction is contracted. So length in the y direction remains the same, that is Ly equal to L0y. Now this is how the area varies. So area A equal to A0 by gamma, where A is the area measured in xy initial frame and A0 is the area measured in x dash y dash initial frame. Similarly for volume, V equal to L into Lx into Ly into Lz, and if its motion is along x-axis, then this will become L0 by gamma into L0y into L0z, which is equal to V0 by gamma. Furthermore, the next thing that we are looking at is its density. Density rho equal to mass by volume. Now at this point, there is something that I need to tell you. The mass of a particle also changes when it is in motion. A particle of mass m0, when its mass is measured when it is at rest, will have a mass equivalent to gamma into m0 when it is traveling at a velocity v. Now, taking that into account, we get equal to gamma into m0 by v by gamma, which is equal to gamma square into v0 by gamma square into m0 by v, which is equal to gamma square into rho 0. These relations need not be by heart. You can derive it, but just in case, I'm showing it beforehand. This is more important for gate than it will be for CSIR. Time dilation equation looks like this. A time period t in this initial frame, a time period t0 in this initial frame is equal to gamma into a time period t in this initial frame. Okay, take note that this is not exactly of the same form as length as the equation for length. For length it was L equal to L0 by gamma. These both are different. Now we move on to Doppler effect. In case of sound, there was a absolute initial frame, right? That is, we had air as our medium. So the initial frame where air is at rest is the absolute initial frame in sound propagation. That is when we talk about sound. But when it comes to special theory of relativity and we are dealing with light, it doesn't matter whether the source is moving towards the observer or observer is moving towards the source. There is no absolute initial frame. So in special theory of relativity, say if we have a source S and a detector D, and the source is propagating some light and the detector is detecting it, the source is propagating this light at a frequency omega and the detector is detecting it at omega dash. Then what happens is this if there is no relative motion between the source and detector, then what we will observe that omega dash equal to omega. But if the source or the detector is moving towards, if the source and detector are moving towards each other, or I always be considered the detector as the moving thing. If the same whether if the source is moving towards the detector as well, if the detector is moving towards the source, then we get at a velocity v. Then what we do is omega dash, that is the frequency as observed by the detector, equal to root of 1 plus beta by 1 minus beta into omega. Alright, so beta is a value which is greater than 0. So the frequency as observed by this as observed by the detector, omega dash will be greater than omega. Now if the detector is moving away from the source, then what happens is, then omega dash will be equal to 1 minus beta by 1 plus root of 1 minus beta by 1 plus beta into omega. Now we move on to our energy study. So say if we have a mass which at rest, say whatever is at rest with respect to me, as if I consider whatever is at rest with respect to me as rest, then if I have a mass m0 at rest, but if that mass which was m0 at rest starts moving, then the mass of this particle actually increases. When it moves, it becomes gamma into m0. This will means new mass, m equal to gamma into m0. Alright. Now, this affects the momentum as well. Momentum p is given as mass into velocity. Right? So, mass is m into v, which will be gamma into m0 into v. This thing affects energy as well. From Einstein's mass energy equivalence, E equal to mc square. So if the particle was at rest, then we would observe E equal to m0 c square. This is its energy that this particle has by the virtue of its very existence of mass. By the virtue of its mass, it has this energy, that is E equal to m0 c square. Alright, that is the total energy of that particle when it is at rest. But when it is moving, when it is moving, E equal to mc square equal to gamma into m0 c square. Now what this comes to is equal to gamma into by Einstein's energy mass equivalence, energy of every object with a mass is given as E equal to mc square. Alright, whether it is at rest or whether it is at moving, whatever the corresponding mass is, into c square is given as its energy. Now, if this particle, this is the total energy of the particle, regardless of whether it is in a gravitational field or whether it is in an electrostatic field. This will be the total energy that it will face. Alright, and this mass, this energy is equal to gamma into m0 c square. m0 is the energy, m0 c square was the energy that it would have had it been at rest. Now, as you can see, there is a difference in energy when it is in rest and when it is in motion. This difference in energy is the kinetic energy that we observe. P equal to mc square minus m0 c square equal to gamma into gamma minus 1 into m0 c square. This might look a bit confusing to you, but at the limit, when v is very less than c, what will happen is this gamma is 1 by root of 1 minus v square by c square. So what will happen is this gamma will become 1 plus half v square by c square minus 1 into m0 c square, which is equal to half v square by c square into m0 c square. This will get cut, equal to half mv square. This is what we observe when v is very less than c. Alright. Now, to take things into further consideration, we can see that energy E is equal to gamma into m0 c square. Now, for instance, if I am squaring this, E square equal to gamma square m0 square c raised to 4 equal to 1 by 1 minus v square by c square, m0 square c raised to 4 equal to v square by c square plus 1 minus v square by c square by 1 minus v square by c square m0 square c raised to 4. I split it, I get v square by c square into gamma square m0 square c raised to 4 mine plus m0 square c raised to 4 is equal to c square, this will take out gamma square m0 square V square C square M0 square C raised to 4 equal to gamma M0V is given as P. So this is P square C square plus M0 square C raised to 4. This is E square. Now this is a very important equation that you will often use in special theory of relativity. Now that's it. That will conclude most of our equations that we will come across. All these things are very important. Whatever I do that, you need to know total energy